Imagine trying to train a 14 billion parameter language model, but you are completely banned from calculating a single gradient.
Oh, wow. Yeah, no backpropagation at all.
Exactly, no chain rule. You are forced to rely entirely on random guessing to update the weights. Historically, attempting that would instantly melt your GPU.
Well, absolutely. And it would take 1,000 years to converge, even if it didn't.
But today, in this deep dive, we're looking at a paper that changes that math entirely. It's called Evolution Strategies at the Hyperscale, and it introduces a framework called EGGROLL,
Which stands for Evolution Guided GeneRal Optimisation via Low-Rank Learning. The authors have effectively solved the hardware bottleneck that kept evolution strategies, or ES, relegated to the fringes of deep learning.
Right, because ES has always been this tantalizing what-if in the background of machine learning. Anyone listening who has dealt with non-differentiable objectives knows the pain.
Oh, for sure. Things like discrete routing, hardware-in-the-loop optimization, or strict outcome-only rewards.
Yeah, gradient descent is just functionally useless in those spaces. You end up relying on proxy metrics just to keep the pipeline differentiable, which is never ideal.
No, it's not.
Yeah.
And ES is theoretically perfect for those rugged optimization landscapes because it doesn't care if the function is smooth.
But we practically abandon it for foundation models because it scales so horribly. So our central mission today is unpacking how you take a mathematical method that demands replicating billion parameter weight matrices millions of times and somehow force it to run efficiently on a single standard GPU.
To appreciate the solution, we have to isolate the exact mechanism of that failure. It's critical to establish that naive evolution strategies do not fail at the billion-parameter scale because of a flaw in the optimization mathematics.
Right. The theory actually works perfectly fine.
It does. The failure is entirely one of hardware utilization. It's a catastrophic breakdown of, well, arithmetic intensity.
Let's contextualize that for the GPU programmers listening. In standard gradient-based deep learning, the vast majority of our trainable parameters are dense matrices. When you use batched matrix multiplication during a forward pass, your arithmetic intensity, which is the ratio of compute operations to memory transfers, is incredibly high.
And that efficiency comes entirely from weight sharing. You load a massive weight matrix into the GPU's high-speed SRAM once, and you reuse those exact same weights across thousands of batched input tokens.
That shared weight paradigm is literally what modern AI accelerators are physically built around.
Exactly. And naive ES fundamentally shatters that paradigm. The core mechanism of ES involves generating a population of slightly mutated models.
So to do this, you create full-rank random perturbation matrices and add them to the baseline model, right?
Yes. And suddenly, every single member of your population has a unique, heavily mutated weight matrix.
Which means you completely lose the ability to batch inputs over a single shared model.
You lose it entirely. Evaluating the fitness of your population forces you to load a unique, multi-gigabyte weight matrix for every single batch item.
Oh man, so your arithmetic intensity just instantly tanks.
It hits a strict theoretical upper bound of 1. You become totally memory-bound. The compute cores on the GPU sit idle, starving for data, because the memory bus simply cannot shuttle those matrices fast enough.
I always visualize this like a traffic problem. Standard backpropagation is like a high-speed train carrying thousands of operations along a single track of shared weights.
That's a great analogy.
Yeah.
Extremely high throughput.
But naive ES takes all those operations and forces each one to drive an individual car on a single-lane dirt road. You hit an immediate traffic jam at the memory bandwidth level.
You really do. I mean, if you're dealing with a 14 billion parameter model and you want a population at the end of 10,000.
You physically cannot materialize and compute 10,000 unique 13 billion parameter models. The VRAM overhead alone is astronomical.
Which points directly to the necessary intervention. Unstructured, full-rank random noise destroys arithmetic intensity.
Right.
Therefore, the search noise has to be mathematically structured to exploit the batching architecture of the GPU. But you have to do it while still preserving the high-dimensional exploratory power of the evolutionary algorithm.
And this brings us to the core mechanism of EGGROLL. Instead of sampling a massive full-rank matrix for the mutation, let's call that matrix E, EGGROLL samples two highly compressed low-rank matrices, A and B.
Right, and it forms the perturbation by multiplying those low-rank factors together.
And the critical implementation detail here is that they never permanently store these mutated matrices, do they?
No, storing thousands of low-rank matrices for a massive population would still overwhelm the system. They actually rely on a counter-based deterministic random number generator.
Oh, okay.
The noise components, A and B, are reconstructed on the fly inside the kernel during the forward pass. The system only stores the random seeds.
So the memory footprint of the entire mutated population is practically zero. Hold on, I want to physically trace the math during that forward pass because this is where the hardware trick actually lives. Normally, you're taking an input vector and computing the dot product against the mutated weight matrix.
Right.
But because EGGROLL defines the mutation as the product of low-rank matrices, you can use the distributive property to split the operation apart.
And that algebraic distribution is the key to the entire paper.
Right.
You basically decouple the static mean weights from the dynamic perturbations.
Okay, walk me through that.
Instead of calculating the input times the mutated matrix all at once, you multiply the input vector by the standard static weight matrix first. Then separately, you compute the scaling factor against the low-rank noise matrices A and B.
I see it. You're adding the low-rank mutation after the main matrix multiplication.
Precisely.
Doing it this way means the heavy lifting multiplying against the static weights can be fully batched again. You've restored the shared weight paradigm for 99% of the compute.
And the remaining computation, handling the unique perturbations for each population member, is reduced to incredibly cheap batched vector products.
Anyone listening who has built inference engines recently is going to recognize this geometry immediately. This is mathematically identical to how systems like VLLM serve thousands of unique Laurier adapters simultaneously.
It really is. You run the base model normally and just bolt on the low-rank adapter math at the very end.
And by structuring the noise this way, EGGROLL achieves up to 91% of the throughput of pure, unperturbed batch inference. That translates to a 100-fold speedup over naive ES.
The throughput is staggering, but it naturally invites skepticism from an optimization standpoint.
I was just thinking that. I spot a massive geometric constraint here. If we use, say, rank 1 perturbations for the evolutionary search, doesn't that inherently restrict our final parameter update to rank 1?
That's the immediate concern, yeah.
Because if we're throwing out gradient descent, we still need the network to learn incredibly complex, full-rank representations. A rank 1 update seems like it would completely cripple the model's capacity.
Well, that intuition makes sense if we were applying a single perturbation, but it misses the mathematical aggregation step of an evolution strategy.
Okay, how so?
You have to separate the search directions from the final update. The individual search directions evaluated during the forward pass are strictly low rank. However, the overall parameter update applied to the model at the end of the step is a score-weighted average across the entire population.
Ah, I see. You are summing up thousands of successful rank 1 mutations.
Exactly. The final update matrix is the sum of n distinct rank R matrices. Mathematically, the rank of that final aggregate matrix is bounded only by the minimum of n times R, or the physical dimensions of the layer.
Right, and because EGGROLL's hardware efficiency unlocks massive population sizes, n can be in the tens of thousands or even millions.
So the product of n and the rank easily exceeds the layer dimensions. The final applied parameter update is mathematically full rank.
So you restrict the shape of the query to save compute, but the aggregate optimization trajectory remains totally unconstrained.
That's exactly it.
Okay, so the hardware architecture is solved. We avoid the memory bandwidth traffic jam and can pump out massive populations. But for the theoreticians listening, fast math is useless if it diverges.
Very true.
We need to prove that a low-rank approximation in a billion-dimensional space actually converges to a useful gradient.
And the theoretical guarantees in this paper are incredibly rigorous. To prove convergence, the authors analyze Gaussian evolution strategies in the high-dimensional limit. That is, as the parameter dimension approaches infinity.
Okay.
They rely heavily on the geometry of high-dimensional spaces, specifically the Gaussian annulus theorem.
Let's visualize that theorem for a second.
Yeah.
In low dimensions, a standard Gaussian distribution looks like a normal bell curve clustered around the origin. But as you scale up to millions or billions of dimensions, the geometry gets bizarre. The probability mass pushes outward, concentrating almost entirely in a thin, hollow shell far away from the origin.
Yes. And because of that geometric shift, if you don't scale your noise variance down as the dimensions increase, your perturbations will instantly explode outward into that thin shell.
And your optimization trajectory will just diverge into chaos?
Exactly. So the authors prove there is a precise geometric requirement. The noise scaling factor must shrink at a rate inversely proportional to the square root of the dimensions.
And under that specific scaling condition, The Gaussian ES update perfectly linearizes.
It does. It converges exactly to the true local first-order derivative of the objective function, even if the underlying architecture or the reward function is mathematically non-differentiable.
That is wild. It creates a direct bridge to the neural tangent kernel, or NTK regime, doesn't it?
It absolutely does. In the NTK limit, we understand that infinitely wide, over-parameterized neural networks behave approximately linearly with respect to their parameters. The paper actually maps out 3 distinct regimes based on how you scale that noise. There's a linearization regime where ES perfectly mimics the first-order gradient. There's a divergence regime where the noise is too large and the update fails.
And the boundary between them.
That's the critical regime. This is where the math gets genuinely exciting.
I was specifically wondering about that critical regime. If your noise scaling perfectly matches the inverse square root of the dimension, the limiting update doesn't just capture the first-order gradient.
No, it doesn't. The Taylor expansion's higher-order terms actually survive the limit, specifically the third-order derivative.
Wait, really? First-order methods like stochastic gradient descent are completely blind to anything beyond a flat slope.
Exactly. But this implies that ES, operating in this critical scaling regime, inherently captures higher-order curvature information.
So it navigates the curvature that gradient descent ignores.
Because an evolution strategy evaluates the fitness landscape holistically, by probing the space geometrically rather than analytically calculating a slope, it can sense the complex contours of the lost landscape.
That makes sense.
Now, applying this to EGGROLL specifically requires another layer of proof, because EGGROLL isn't using true dense Gaussian noise. It uses the product of sub-Gaussian vectors.
So how do they bound the error introduced by that approximation?
They utilize Edgeworth expansions to bound the difference between the low-rank distribution and the true Gaussian distribution. They definitively prove that the EGGROLL update converges to the true full-rank Gaussian ES update at a fast rate.
I think the paper said it's bounded by big O of the inverse ring.
Yes. Furthermore, they prove that in the high-dimensional limit, EGGROLL perfectly linearizes to the true gradient, even if the search rank is restricted to exactly 1.
A rank 1 search perturbation provides a mathematically consistent gradient estimate in a billion-dimensional space. That is a stunning theoretical result.
It really is.
But theory only takes us so far. To truly prove that this algorithm can do things gradient descent cannot, you have to apply it to an architecture that breaks backpropagation completely.
Oh, and they do. Which brings us to pure integer pre-training.
This is perhaps the most audacious empirical test in the entire paper. The authors design a model called EGG, the Evolved Generative GRU. It's a 6-layer, 256-dimension, nonlinear recurrent network.
And the defining characteristic of EGG is that it operates exclusively in Ichigo 8 data types.
When we say exclusively, we mean there is no hidden floating point math acting as a crutch. It never casts to FP32 or BF16 at any point in the forward pass.
None at all.
But the most extreme architectural choice is that they completely stripped out all explicit activation functions. No ReLUs, no SciLUs, nothing.
They remove them entirely. Instead, they rely exclusively on the implicit nonlinearity that happens at the hardware level when an 8-bit integer overflows or is aggressively clipped at its maximum boundary.
Think about the calculus of that for a second.
Yeah.
You physically cannot backpropagate a gradient through hardware-level integer clipping.
You really can't.
A hard mathematical clip means the derivative is literally 0 everywhere, except at the exact threshold of the clip where it is completely undefined. A gradient-based optimizer looks at that landscape and sees a completely flat, infinite dead zone.
It has 0 signal to learn from. Gradient descent is totally blind in this environment.
Right.
But this is where the geometric nature of an evolution strategy shines. Because EGGROLL is so computationally efficient, the authors scaled the population size up to over 1 million parallel generations per single update step.
Wow. But how does evaluating 1 million models suddenly capture a signal from a dead zone?
Well, an evolutionary algorithm isn't calculating a local slope. It's basically blindly feeling around in a dark room.
Ah, I see.
By evaluating over 1 million slightly mutated parameters simultaneously, it maps the physical edges of the box. It finds the exact phase transition where the integer clips or overflows.
So it takes a mathematical dead zone and turns it into a geometric map of fitness.
Exactly. And the empirical results validate that geometric mapping. This pure integer EGG model, trained entirely without gradients, relying only on integer clipping for nonlinearity, actually outperformed a standard FP32 transformer on the Minipile dataset.
That's incredible. The EG model achieved a test loss of 3.40 bits per byte compared to the transformer's 3.58 bits per byte.
It is a profound paradigm shift. We have generally assumed that you need high numerical precision to maintain stable optimization trajectories.
But this proves that massive compute scaling evaluating millions of parallel rollouts can completely compensate for extreme quantization.
And structurally non-differentiable architectures, too. It demonstrates that if you can evaluate the forward paths fast enough, the evolutionary search can navigate landscapes that the chain rule simply cannot traverse.
Pure integer pre-training is a fascinating proof of concept, but if you're managing a production ML pipeline today, your most pressing problem is likely post-training large language models for complex reasoning.
Oh, without a doubt.
This is the domain dominated by reinforcement learning algorithms, specifically Group Relative Policy Optimization, or GRPO, which OpenAI popularized with their O1 models. If EGGROLL is truly viable, it has to compete at the hyperscale against modern RL.
And the authors address this directly. They used EGGROLL to fine-tune RWKV7 foundation models, scaling up to 14 billion parameters on the DeepScaler dataset.
That dataset is focused on highly complex mathematical reasoning tasks, right? Like AM and GSM-8K.
Yes. Yeah.
Using RWKV makes a lot of sense here. It's a recurrent architecture with a constant state size, meaning it avoids the massive memory overhead of the key value cache you'd normally struggle with in transformer rollouts.
That's a great point. That lets them push the population batching even higher. And when comparing the results, EGGROLL matches, and on several metrics exceeds, the reasoning performance of GRPO.
That's huge.
But the critical takeaway is why EGGROLL is so competitive at scale. It comes down to the optimizer memory footprint. Algorithms like GRPO rely on the Atom optimizer to apply the final policy updates.
Anyone who has tried to tune a massive model knows that Atom is just a colossal memory hog.
Oh, absolutely.
To compute its updates, Atom has to maintain the first and second moments, the running average of the gradient and the uncentered variance for every single parameter. If you have a 14 billion parameter model, Atom requires tens of gigabytes of VRAM just to store those optimizer states.
And that memory overhead creates a severe bottleneck for reinforcement learning. It artificially limits the number of parallel generations GRPO can hold in memory during the rollout phase.
Right.
EGGROLL, by its nature, does not carry Atom state memory during the evolutionary search. This lack of optimizer bloat allows EGGROLL to run vastly more parallel generations.
So on the exact same hardware footprint where GRPO might be heavily constrained to evaluating just 256 parallel paths, EGGROLL can effortlessly evaluate, what, 8,192 parallel generations?
Exactly. You are exploring thousands of more reasoning trajectories per single update.
And if you look at the math of how EGGROLL scores those trajectories, there's a fascinating parallel to RL. EGGROLL's scoring function normalizes the fitness of the population across a batch of questions using global variance.
Yes.
Mathematically, that mechanism is essentially identical to the group relative advantage calculation that gives GRPO its name.
The variance reduction technique is fundamentally the same. You center the rewards around the batch mean to stabilize the update. The true differentiator is not the scoring logic. It is the raw scale of parallelization that EGGROLL's low-rank architecture unlocks.
Furthermore, because EGGROLL is an evolution strategy, it completely frees the post-training pipeline from the requirement of a differentiable loss landscape.
Which fundamentally alters how you design your reward functions. In standard reinforcement learning, you typically optimize for zero-shot accuracy, what we call pass at one.
Because you need a dense, differentiable adjacent signal to effectively approximate the policy gradient.
Right, exactly. But because EGGROLL only requires discrete outcome scores, the authors directly optimize the model for pass at K.
So instead of penalizing the model if it fails on the first try, the fitness score only evaluates whether the model eventually arrives at the correct answer within K distinct attempts.
And optimizing directly on that metric profoundly shifted the model's behavior. The data shows that optimizing for pass at K dramatically increased the diversity of the reasoning paths the model explored.
That makes total sense. When you force a model to optimize for pass at 1, it tends to undergo mode collapse, converging onto a single, safe, highly generic reasoning trajectory.
Right. Pass K encourages the network to generate multiple, mathematically distinct logical approaches to the exact same problem.
It's also worth noting they proved this capability on strictly discrete environments outside of natural language as well. They took a time series foundation model and fine-tuned it for high-frequency trading.
Oh, that was a brilliant test.
Rather than training on proxy metrics like price prediction, they used EGGROLL to optimize the model directly on P&L profit and loss. A P&L calculation is computed through a complex matching engine simulator.
It is an entirely discrete, step-by-step software environment. It is completely non-differentiable.
But by optimizing the P&L directly, the EEGROLL model yielded a 155% improvement over the baseline.
It just confirms that whenever you have an objective function locked behind a complex, non-differentiable simulator, high-throughput evolutionary search is highly effective.
So, to summarize the magnitude of the engineering and theoretical leaks we've covered today, the authors of this paper have systematically dismantled the arithmetic intensity bottleneck that historically crippled evolution strategies.
They really have.
By designing on-the-fly, low-rank parameter perturbations, they mimic the extreme compute efficiency of batched LoRa inference, unlocking a 100-fold throughput speedup on modern GPUs.
And they back that architecture with rigorous proofs, demonstrating that under the correct high-dimensional noise scaling, this low-rank approximation perfectly linearizes.
It converges to the true first-order derivative in the NTK limit, even if the search rank is restricted to 1.
And they empirically validated the framework by doing things backpropagation mathematically cannot do.
Like successfully pre-training a pure integer activation-free neural network by mapping geometric bounds with massive populations.
And fine-tuning a 14 billion parameter reasoning model that matches state-of-the-art RL by directly optimizing discrete, non-differentiable rewards at hyperscale.
It really forces us to reconsider the absolute necessity of the chain rule. We now possess a mathematically sound, highly hardware-efficient alternative for updating billion-parameter networks, which leaves us with a massive forward-looking implication to consider. If EGGROLL allows us to efficiently train massive models without calculating a single gradient and directly optimize for discrete software outcomes, well, what happens when we stop building homogeneous, continuous neural networks?
That's the big question.
What happens when we start embedding strict, compiled software tools, discrete logic engines, or rule-based symbolic simulators directly inside the internal layers of a model during the pre-training phase?
It changes everything.
If the pipeline no longer requires end-to-end differentiability, are we finally looking at the computational foundation for scalable neurosymbolic AI?
For the last decade, we have constrained our architectures to fit the requirements of backpropagation. EGGROLL suggests we might finally be able to build architectures that fit the requirements of the problem.
Something to think about the next time you design a loss function.